Everyone, so in this video I'm going to go over the fundamental principles of valence bond theory or hybridization. So the main idea behind valence bond theory is that bonds are localized between adjacent atoms. So that's really important for you guys to keep in mind. So we're talking about two adjacent atoms sharing electrons to form a covalent bond. Okay, so one of the things that we need to think of is, okay, if we are talking about, once again, organic compounds, the backbone of every organic molecule is a carbon atom. Okay, so this is the valence shell for the carbon atom, right? So we have shell number 2 with 4 electrons in the valence shell. So if the bonding, according to valence bond theory, were to happen by just carbon bonding to other adjacent atoms, let's say hydrogen atoms, then obviously we know that the angle between the p orbitals is 90 degrees. I'm going to just draw here a basic, uh, very simple organic molecule, let's say the molecule of methane. So if carbon were to use its atomic orbitals to form bonds, four bonds to four hydrogens here, obviously, because the angle between the p orbital is 90 degrees, then you would be expecting the angle between these bonds to be also 90. In reality, that's not the case, and we know that the angle between these bonds is actually 109.5. Therefore, um, this idea of carbon using just its pure atomic orbitals for bonding is not really good. It doesn't explain the experimental fact of the bond angle in organic molecules. So to account for this difference, uh, Linus Pauling came up with a different theory, which is what we call today hybridization. And this says that before bonding, I'm going to write it over here. So before bonding, the atomic orbitals, in this case of carbon, are combined, or let's say a new word, hybridized, to form new hybridized orbitals. And these hybridized, or these hybrid orbitals, are the orbitals that are actually used for bonding according to valence bond theory. So according to valence bond theory, guys, carbon atoms, or the atoms in general, are not using their pure atomic orbitals for bonding. They instead are using hybrid orbitals for this bonding. So how are hybrid orbitals generated? So hybrid orbitals are created from the mathematical combination of atomic orbitals in such way that if we combine, in this case for carbon, 4 atomic orbitals, we will always get 4 hybrid orbitals. Therefore, we can say that the number of hybrid orbitals formed equals the number of atomic orbitals combined. So if we combine 4 atomic orbitals, we are expecting to get, obviously, 4 hybrid orbitals. Okay? Remember, we have discussed in class uh, a little bit about quantum mechanics, and when we're talking about combining atomic orbitals, remember each of these orbitals is a solution for the Schrodinger equation, so combining them simply means mathematically adding these 4 solutions to create 4 new solutions of these equations, and that's what we call the new hybrid orbitals. So how can carbon, or how many different ways do we find for carbon to be hybridizing its atomic orbitals to form new bonds? Okay, so the first most common way to find this, I'm gonna just lower down here the energy diagram. Once again, remember, I'm ignoring the 1s orbital because we care only about the valence shell. Those are the valence electrons, are the only one participating in reactions. Okay, so if we combine, one possibility for carbon is when it combines its 4 atomic orbitals, and in that case, combining 4 atomic orbitals, as you should expect now, will lead to 4 hybrid orbitals. Always we get the same number, right? So it's gonna write here the so combining 4 atomic orbitals will lead to 4 new orbitals, and these new orbitals, because we are combining 1s and 3p, we call them sp3 hybrid orbitals. Okay, so combining once again 1s orbital and 3p orbital leads to 4 hybrid orbitals, and these new hybrid orbitals are called sp3, resulting from the combination of 1s and 3p. Now the total number of electrons here for carbon is 4, so we fill up these hybrid orbitals with 1 electron in each case, and that leads to 4 sp3 hybrid orbitals, each one having 1 electron. Therefore, as you can imagine, then carbon is expected to form 4 bonds. Okay, a carbon with 4 single bonds is a carbon that is sp3 hybridized. And this sp3 hybridization, so these sp3 hybrid orbitals, the 4 of them, are the ones that carbon is using for bonding to other atoms, in this case 4 hydrogens. Okay, so what is the geometry of an sp3 hybridized carbon? So an sp3 hybridized carbon is tetrahedral. So remember we just discussed about the combining mathematically the 4 atomic orbitals, forming 4 new hybrid orbitals. So if the solution for these combinations, if you plot them, they result in 4 sp3 hybrid orbitals, and plotting them together, you will find that the angle between all of them is 109.5. Okay, so that will be the case for a carbon atom. I'll give you another example of, let's say, a hydrogen atom. So, nitrogen sp3 hybridized. So, let's say a molecule like ammonia, where we have once again the nitrogen with a lone pair. So this we should know from Lewis structure. So in a case like this, once again, we have the nitrogen bonded to 3 hydrogen atoms. All that we see here is single bonds, guys. If all we see is single bonds, the atom will be sp3 hybridized. So for nitrogen, once again, the nitrogen has 4 electrons in the valence shell. So combining 4 orbitals, in the valence shell, combining 4 orbitals leads to 4 hybrid orbitals, sp3 hybrid orbitals. The total of electrons in the valence shell of nitrogen now is 5, so I'm going to add 1 here. Therefore, I need to place 5 electrons in the new hybrid orbital, so I'm going to add a 5th electron here. So this, as you can see here, what is showing you is that for the nitrogen, an sp3 hybridized nitrogen has 1 sp3 orbital, which is actually full. That's the one where the lone pairs of nitrogens is going to be located, and 3 sp3 hybrid orbitals that would be available for bonding. In this case, each one of them is used to bond a hydrogen atom. Okay, so once again, the geometry of an sp3 hybridized nitrogen is also a tetrahedral structure. Okay, in this case, remember the 4th sp3 orbital, hybrid orbital, is occupied by a lone pair, so the angle is slightly lower than 109.5. It's in this case 107. But anyways, the point being is that it's the same hybridization for the carbon than for the nitrogen. It's sp3. Only difference is that in the case of the nitrogen, one of these hybrid orbitals is occupied by a lone pair. And we can extend this same reasoning for the oxygen atom. So let's say if we have an oxygen atom here, for example, the molecule of water, which is the classic example. Okay, so water, oxygen obviously will be having 2 lone pairs. Oxygen has in the second row of the periodic table, valence shell is shell number 2, 4 orbitals. So combining 4 orbitals here leads to 4 hybrid orbitals. These 4 hybrid orbitals will be having now 6 electrons, because that's the valence electrons, the number of valence electrons for oxygen. So I'm going to add one extra electron here. And then I need to then place the 6 electrons in the hybrid orbital. So we'll be adding one extra one here. So that's 6 electrons in the valence shell, 6 electrons in the hybrid orbitals of oxygen. So as before, same thing. We have now 4 sp3 hybrid orbitals. So this oxygen has no pi bonds, it's all single bonds. The moment you see atoms with all single bonds, that atom is sp3 hybridized. So therefore, sp3 hybridized atoms will have 4 sp3 hybrid orbitals around them. In this case, 2 sp3 hybrid orbitals are available for bonding, one to bond each of the hydrogen atoms, and the remaining 2 sp3 hybrid orbitals are fully occupied with the lone pairs of electrons. So once again, in the molecular water, the lone pairs of electrons are located in sp3 hybrid orbitals. You can see the geometry of a water molecule here is tetrahedral structure, same thing once again, because now we have two lone pairs of electrons. The repulsion between these lone pairs make this tetrahedral pyramidal structure to shrink a little bit, resulting in a bond angle here of about 105 degrees. Okay, so that's how you envision sp3 hybridization for carbon, nitrogen, and oxygen atoms. Okay, so what happens with what's the next way in which we can find an atom, carbon atom, let's say, hybridizing. So another possibility could be in that in which you have an organic molecule with a carbon atom or an oxygen atom, remember it doesn't really matter, having one pi bond. Okay, so let's copy the valence shell of carbon to repeat our analysis here. I'm gonna bring it over here. So let's say we have an organic molecule like this. Okay, so we have 2 carbons here. Let's add 2 hydrogens over here. And 2 hydrogens on the other carbon. So in this case, let's see how is hybridization happening for a molecule like this, for the carbon atoms. Okay, so this carbon atom here and these carbon atoms here, both of them, they have 3 sigma bonds and they have 1 pi bond. And remember, guys, how by definition a pi bond is side by side overlapping of pure p orbitals. So if there is a pi bond, so one of the p orbital of the pure p orbital, so the carbon atom, must be used exclusively for the pi bond. So we're gonna save this pure p orbital here for the pi bond, because there is a pi bond there, and we understand that the pi bond is a result of side-by-side overlapping of pure p orbital. So I'm gonna leave this p orbital here, and I'm gonna place 1 electron in this p orbital, which is the one used for this pi bond. So if 1 p orbital is being used for the pi bond, how many orbitals, atomic orbitals in carbon do we have remaining? 3, 1s and 2p. So combining 3 atomic orbitals, 1s and 2p, will lead to, once again, 3 hybrid orbitals. And in this case, we are going to call this sp2 hybrid orbitals. Okay, combination of 1s, once again 1s and 2p, that's a total of 3, right? And 3 orbitals will be sp2. So I'm going to say over here 3 sp2 hybrid orbitals, sp2, sp2, and sp2. So these 3 sp2 hybrid orbitals. So this carbon atom here over here, when you think about the orbitals using for bonding, so this carbon have 3 sigma bonds. The 3 sigma bonds for these carbons are made through the 3 sp2 hybrid orbitals. Look at how each of them has one, there is room in each of them available for new bonding, right? And the 4th bond of this carbon is a pi bond, which is through the pure p orbital. Okay, so the geometry of an sp2 hybridized carbon is trigonal planar, meaning that, and I have the picture here, meaning that the molecule is flat. You can see how the angle between here, the sigma bonds here, This angle is 120 degrees, right? The angle between each sigma bond is 120. The molecule is flat. You can see the plane of the molecule here in blue, meaning that all the sigma bonds, guys, are in the same plane, right? And then above and below the plane, you have the pi bond here showing red and blue. Remember, the color only refers to the sign of the wave function. The angle, guy, between the pi bond and the sigma bonds, you can see how it's 90 degrees. This is very important, right? So the angle between all sigma bonds is 120. Angle between the pi and sigma is 90 degrees, right? So the molecule is flat, and above and below this plane of the molecule, you will have a cloud of electrons corresponding to the pi bond. So that's for sp2 hybridized atoms. Once again, when do you have an sp2? Whenever there is one pi bond. Could be carbon, or it could be in an oxygen atom, or any other heteroatom with a pi bond will have an sp2 hybridization. And then the last way for a carbon atom to hybridize its atomic orbitals is when you have a molecule in which the carbon atoms are having a triple bond. Okay, so in that case, a triple bond means, once again, remember how we learned in class before that whenever we have that a triple bond, one bond is sigma and two bonds are pi. The reason for that is obviously there can be only one sigma bonds between two atoms. They are the result of direct overlapping of hybrid orbitals in this case. So if you have a triple bond, one sigma, and two of them will be pi. So if we have two pi bonds, obviously then we need to save two p orbitals for those two pi bonds, and there will be one electron in one of these p orbitals for the corresponding pi bond. And then combining, if you have two p orbitals used for two pi bonds, you are left with only two orbitals out of these four for hybridization. So combining one s and one p, that leads to two hybrid orbitals, both sp, and that's what an sp carbon is. Once again, look at an sp carbon hybridized. It has two sp hybrid orbitals, which could be used for bonding to another atom, and it has two pure p orbitals for the two pi bonds. So when you look at this carbon here, this carbon is bonding through to this carbon on the right using one sp hybrid orbital for the sigma bond, and it's two p orbitals for two pi bonds. And this carbon is bonded to this hydrogen through a sigma bond, and the orbital from the carbon in that sigma bond is an sp hybrid orbital. So the hybridization of an sp orbital is an sp hybridized atom is a linear, meaning that the angle between the sigma bond is 180. Remember that the angle between the pi bond is always 90, so you have like a cylinder of electrons around the sigma bonds, since once again the angle between both pi bonds is 90 degrees. That's the angle in between p orbitals as well. Okay, so this is how you reason hybridization for carbon atoms. You can apply the same reasoning to other atoms. Once again, carbon atom with four single bonds or any atom having just single bonds will always be sp3 hybridized. The geometry is tetrahedral. Carbon atom with one pi bond will always be sp2 hybridized. That pi bond is through a pure p orbital. The three sigma bonds for this carbon will be done using sp2 hybrid orbitals, and the angle between the sigma and the pi is 90 degrees. And if you have a carbon with a triple bond, two of these bonds will be pi, so two p orbitals used for these two pi bonds, we can only combine one s and two p, and one p, I'm sorry, so that's sp hybridization. So two sp hybrid orbitals and two p orbitals for the two pi bonds. So I hope this helps, and thank you.